Well, we have a new catchphrase for you to put in your energy vocabulary. That is carbon recycling. This is technology that converts CO2 into liquid fuel that can then be recycled instead of simply being discarded. Carbon Sciences is a relatively new company, only 3 years old, based in Santa Barbara, California. And the team there says carbon is not the problem, but rather it is the solution to the nation's energy concerns. And Carbon Science says it should be ready to unveil its product potentially early next year. Joining us now to talk about this breakthrough technology is Byron Elton. He is president and CEO of Carbon Sciences in town today from Santa Barbara. Byron, good to have you with us today.
Thank you, Tyler. Good to be here.
Put it in a nutshell. You have said we transform carbon dioxide into other fuels, and we do it in a matter of hours. This is extremely complex technology, though.
It is. You know, the president, you were referencing President Obama earlier, in his inauguration speech, he said that each day brings new evidence that the ways we use energy strengthen our adversaries and threaten our planet. And we couldn't agree more. And we have some serious challenges ahead of us, both in terms of energy and in terms of climate. And so the question is, how are we going to continue to obtain the kind of energy that we need and be good stewards of the environment? And Carbon Sciences has a technology, as you mentioned, that takes carbon dioxide as its feedstock and through a proprietary biocatalytic process transforms it into gasoline and other liquid portable fuels.
Am I simplifying it, Byron, to say that you're protecting the biocatalysts within the CO2 and then using them for energy later?
That's exactly right. The transformation of the carbon and the hydrogen into hydrocarbons, which are the building blocks of fuel, happens where the biocatalysts actually interact with both. Now in nature, and this process essentially emulates what happens in nature, it happens over long periods of time. These biocatalysts are very focused, very single, they have a great appetite for carbon. But in nature, they work very slowly. They actually perform very few of their missions before they're either depleted or exhausted. And so our technology actually provides a protective environment where the biocatalysts can do three things that they can't do, or better than they do in nature. One is they thrive and exist for long periods of time. So they're able to perform their missions over and over again. And because they're protected, they can do it very efficiently, faster, and actually perform more cycles, more turns than they normally would. And so that's our ability to transform the carbon dioxide into the liquid portable fuels in a matter of hours as opposed to millions of years.
The problems we have discussed at length, Byron, regarding carbon capture and storage or sequestration is simply the capture stage and then the sequestration stage. How do you capture your CO2? Where is that feedstock coming from? And can you translate that into a capture process from a major CO2 emitter? So
our business is not the carbon capture. There's plenty of people who are working on that. And the obvious candidates are the large emitters of CO2. That's anybody that's burning lots of stuff and throwing CO2 into the air. Coal-fired plants being obvious candidates for that, but natural gas, cement plants, refineries. I got a call the other day from a limestone quarry in Missouri who said he throws enough CO2 into the air that he could make 700,000 gallons of gasoline every single day with our technology.
And that would be your feedstock to some degree getting pumped in?
Absolutely. And so the technology would be co-located at the site of the emissions. And once the carbon dioxide is captured, then our technology comes into place, the biocatalytic process, and turns it into the fuel. There's wonderful work going on in so many approaches to solving these problems, certainly in biofuels and algae, wind, solar, tidal, all of that.
All of the above, as we call it in Washington.
All of the above. And these are enormous challenges, and the solution needs to match the enormity of the challenges. It won't be one single solution. It'll be an aggregate of all of these. But we bring some dynamics to the approach that we think are very compelling. One is, ours is the most direct path from CO2 to fuel. We go CO2, biocatalytic reaction, into the fuel. That's number one. Number two, because it's a biocatalytic reaction, it's done at very low energy. We essentially do it at room temperature and atmospheric pressure, and therefore very, very low energy. We have a prototype right now in Santa Barbara where you could come in, and we hope you'll come and visit us and see that happening. Third, and this is very important, it fits right back into the existing infrastructure, the existing supply chain, the existing vehicles. So there's no additional money or capital expenditures needed to provide special machinery, special supply chain for this. And then last is scalability. There's lots of ways of providing alternative fuel, but very few that can really make a big impact. Because the supply of carbon dioxide is so enormous and getting bigger every day, the ability for us to make copious amounts of fuel is extraordinary. We've actually done some math on this. We're only at the prototype stage. But if we think about the coal-fired plants, which are the #1 emitter for CO2, with less than half of what they'll be putting out in the next 20 years, with our process, we could make enough fuel to furnish 30% of the global fuel, liquid portable fuel needs.
Byron, two-part question on efficiency. First of all, the physical process. 65 cubic feet of CO2, along with 10 gallons of water, that will produce 1 gallon of gasoline or gasoline equivalent, correct?
That is correct.
Do you intend to improve that efficiency, or is that a model you can work with effectively on a large scale?
Well, we believe we can. Again, right now it's in the prototype stage, and we're making vials of methanol right now. We have filed patents this year, more patents coming that discuss and describe and protect these procedures. So right now we're making small amounts of methanol. The modeling that we've done suggests that exactly what you said, 65 cubic feet of carbon dioxide, 10 gallons of water, we can make a gallon of gasoline. If we take that to a metric ton of carbon dioxide, we can make 150 gallons of gasoline. Now you start thinking about the fact that there's 30 billion metric tons of CO2 being emitted into the atmosphere every year, and the estimates are that that's going to be over 40 by the year 2030. A seemingly inexhaustible, no pun intended, inexhaustible supply of CO2 for the process.
What about what I would call the macro efficiency here? That is the energy expenditure that goes into simply making the fuel. Any kind of biofuel or equivalent generally requires a great deal of energy just to produce.
Great point, and it's sometimes something that's overlooked when we consider, as they would say on Madison Avenue, is the juice worth the squeeze? And because again of the biocatalytic reaction, and again it's done at room temperature, atmospheric pressure, very low energy output. We're not growing things, we're not expending large amounts of water, there's no harvesting involved. Again, that direct path from CO2 to fuel that makes it very energy efficient.
What about the timeline, Byron? And depending on the source, you get different stories about carbon capture and storage. Jim Rogers with Duke Energy has talked about 2015 being his not firm deadline, but the goal he would like to see for proven CCS on a commercial scale. Branko Terzic, former FERC commissioner, was here last week saying, no, it's more like 2020 where we're going to see CCS. Are you in a race with that technology to get on an economy-wide or a large-scale proven system?
So again, we're not in the carbon capture business, but
right, but it's a competition to some degree. Do we store it or do we recycle it?
That's right. So in terms of our own internal timelines, we launched the prototype in the first quarter of this year. We'll be working with that and gathering data through the year. We believe that next year we'll be ready to move into a mini pilot stage. Now that's a demonstration of the prototype, of the technology on a much larger scale. So we'll be making lots of fuel, lots of gasoline. And then of course gathering the data to prove and model up that we can do this with a strategic partner, we believe by 2011, in 2 years. Now, in terms of the availability of the CO2, again, if you're a big CO2 emitter and you're either being forced to capture that CO2 and then do something with it. If your only option is then to sequester it, and there's all kinds of concerns and questions about, is that a good idea? Right. Or the ability to take it, turn it back into a very valuable, usable liquid portable fuel, we think that the choice is fairly simple in that case. This fellow that I talked to in Missouri said 700,000 gallons of gasoline. Now he's got to capture that carbon first, that carbon dioxide. Wanted to jump on a plane and come out to Santa Barbara immediately. Said, not so fast, cowboy. We've got some work to do. But we believe that the ability to have this technology available is going to accelerate the need and the ability and the desire for them to capture that CO2 and use it in this sense.
Now, Byron, I need you to explain the term strategic partner. Are you looking for public financing here, something like the DOE with a large-scale loan guarantee, or is this private investment?
We're actually publicly traded, CABN is our stock symbol, and we do have private investors that allow us to continue the research. The strategic partner will really be, so for instance, the mini pilot. We will be working with a strategic partner to help fund and to do all that research. And then the first opportunity in the field, once that technology has been proven on that scale, we'll be looking, and we've had lots of inquiries and lots of conversations with people from around the world, quite frankly, want to do it in the United States, where we will then co-locate this facility on the premise of where the CO2 is being emitted, and show it on a large scale and prove it to the rest of the world. And then we license the technology to anybody in the world that's emitting CO2 and would like to have this additional revenue stream or produce fuel for themselves.
2011 is the time frame we're looking at. Byron Elton is President and CEO of Carbon Sciences. As we said, groundbreaking technology underway in Santa Barbara. Byron, thanks for making us part of your DC tour.
Thank you, Tyler.
We'll stay in close touch.
Okay.